This problem sort of presents a nice twist and combination of many things we've been talking about. There's an object on an incline here, incline at an angle theta, M2. Rope attached to it goes over pulling, is attached to a hanging mass over here, M1. So the questions are the same here, depending on what the problem might be, but at sort of a fundamental level, you want to know, well, what is the acceleration of the two blocks, and what is the tension in that rope there? So we'll see if we can go about doing that. So once again, Newton's laws are here, ready, available to go. We're going to identify the forces. We're going to put some signs in there, and we're going to go ahead and fill in the equations 1 and 2 and see what we get. So the first thing we'll do then is let's go ahead and identify those forces on these masses. M1 is probably the easy one because it's hanging here. We'll say this has a mass M1G and an upwards pull T, like that. Tension pulls up, weight pulls down. M2 is the next one here. There's several forces on it, I guess. We can put its weight in here. Here's an M2G. It is sitting on a surface, so it's going to cause that surface to flex. There will be a normal force up on it like that. And there will be a tension pulling away from N2 like that. And it's the same tensions in the other side of the rope. It's going to pull straight down like that. So if you're sort of in a hurry, you're not really paying attention, you might conclude that you're done. Those are all the forces, but there is one more. Even though M2 is sitting on an incline, even though it has a rope attached to it and all these things going on, remember, it still has a natural tendency to want to slide down the incline. So we're going to go ahead and not forget that there is a sliding force pulling down on M2. The sliding force is not a fundamental force, it's a component of gravity. But if you can sort of remember sliding force as mg sine of theta, or in this case m2g sine theta, it can save you a few steps to get the problem done. So here we go. Those are all the forces. Let's put those signs in now so we can proceed with filling in Newton's laws. So some of the signs that could happen here are, let's just go ahead and call down the incline negative, so that'll be a negative t. If that's a negative t, that'll be a positive t because it's on the opposite side of the rope. And we're going to call this t negative. The sliding force will also be negative. And if t is positive and upwards, m1g will be negative and downwards like that. So I think that's a nice sign convention, and it's consistent. If m1 moves down, that's a negative direction. Just like if m2 moves down the incline, that's a negative direction since negative is that way. So it's a nice and consistent sign convention that we have in there. And I think that's about all we're going to need right now. So let's just proceed and see how the problem works itself out. Okay, so what we'll do then is we'll look at mass m1. Nice and easy, just sitting here. There are no x forces, only y forces. So that means the y acceleration on this block here is going to be plus t minus m1g divided by m1, something like that. There's the y acceleration on that block. You can put a big box around it because you've got it. Nothing much else to say about it. What we'll do now is go ahead and proceed with that mass m2. Look at those forces on it now as well. As usual, there's usually a bit of confusion with these incline problems about where the coordinate axes is exactly here. What do I call x and what do I call y? Well, remember, typically we put one axis along the axis of motion. We'll call that the x-axis, and the y-axis right there, something like that. So we'll go ahead and put that in there. Those are the x-y coordinates, so now we can apply Newton's law, say, along those coordinates. So what we'll say then, we'll look at the x acceleration first. The x acceleration then is going to be a combination of a couple of forces here. So here's your a sub x in here. Sum the forces again. I have a sliding force down the incline, minus f sub s. I have a tension down the incline, minus t, like that. I don't see any other x forces on it, except for this one and this one. There's nothing, say, pulling up that way, like some friction or another rope. There could be another problem, but there isn't right now. And I'll just divide all that by m2. That's my x acceleration. And lastly, I can look at the y forces on the same block sitting on the incline. And in particular, I have a normal force up, and it looks like that might be the only y force on the block, but in fact there's another one. It's a component of gravity in here. So if I look very carefully, here's that right triangle, which we've sort of completed in another video, which you can look at here. But in particular, the way this always works out here is if gravity is this red arrow going down like that, and this is angle theta, there's going to be a theta in there too. And this side over here is going to be m2g times the cosine of theta. So it's the cosine. And notice that this side over here is going to be m2g times the sine of theta. And in particular, two bits of information pop out of this. m2g sine of theta is parallel and down the incline. That is the sliding force that we hypothesized exists here early in the problem. So when we go filling some things in just a minute here, we'll have something about the sliding force. But let's go ahead and finish up this AY right here. In particular, we'll notice that in the Y direction, it looks like we have a normal force straight up. So here's the Y-axis right here. and this normal force, which sort of got covered by my green line, is still straight up like that. There's that capital N, straight up like that, the normal force positive, and I'll call the M2 cosine theta over here negative since it points down that way. So I'll have an N right there, and I'll put a minus M2G times the cosine of theta. Those are the forces along the y-axis, and I'll divide this whole thing by M2, and there's my y acceleration, so I can put a big box around that, and I have it. Put a box around this as well, so those are the three equations that were generated from Newton's laws. There's one for M1 and two for M2, and we still have a little bit more business to take care of before this will be all sort of wrapped up here. So the first order of business here is, what are you going to put in for Fs right here? Well, Fs sort of popped out of this triangle here, or you can just sort of commit it to memory that the sliding force is always M2G sine theta. So this equation here, we'd always fill in for Fs is going to be M2 times G times the sine of theta. Okay, that's the sliding force. Came right out of there. Also in this equation for a sub y right here, we have, no, I guess we don't need to bother with that. I think we're done with this. It's just the sliding force gets plugged in with this, and I think we'll be right at our solution here. So what we'll do is a bit of an intuitive step, which we always have to do in these problems. In particular, that the y acceleration of this block is the same as the x acceleration of this block because they are linked by a rope. So this a sub y right here is the same as this a sub x right there. So what I'll do in this case is you could rewrite them with an a, but what I'll do is I'm just going to put the two equations together and say, because it's the same a over here, I'll say plus t. Looks like my pen is dying here. Get another one. I'll say plus t minus m1g divided by m1 is equal to minus m2g times the sine of theta. That's what I just filled in for the sliding force right there. No problem. Minus t divided by m2, like that. So I get this big ugly equation here, but you're good at algebra, and so what you can do in an equation like this here is just solve it for t. Solve it and get the tension out right there. So you'd have that tension in this rope here. It's all done. You got it for you right in front of you there. There's the tension. Now if you wanted the acceleration also, just like in the other problems, you just can go back and use the other equations to find the tension. In particular, you could say go back to this equation right here. Once you have this t, you could plug it into that t right there and get an acceleration to pop out. So it's all nice and consistent. It should work out. But from these equations that you have drawn here and that intuitive step that a, y, and ax are the same because the two objects are connected by ropes, you should be able to solve for t directly from this big equation that's formed here, and you should be able to get the acceleration of the system to come out.